In this video, we're going to look at more examples where we are going to try to identify the continuity of a variety of functions. So let's start with the function f of x equals 5 over x. When I think about continuity, I usually think about or ask myself, is there any spot that is going to be problematic? Right? And so when we're dividing by something, if that thing that we are dividing by is equal to 0, then that is potentially a problem. And so we might have a problem when x is equal to 0, and indeed we do. When x is equal to 0, we're going to have a vertical asymptote. So this function looks kind of like this. You have a vertical asymptote at x equals 0. So you have this discontinuity at x equals 0. What kind of discontinuity is that? Is that removable or non-removable? Because it's not just a hole in the graph, there's no way we can just fix that. We can't just patch it up. This is a non-removable discontinuity. And so this function is continuous on negative infinity up to 0, union together with 0 to infinity. So at 0 itself, it is not continuous, but it is continuous everywhere else. What about this next function? G of x equals x cubed minus 4x squared plus 2x plus 1. Are there any values that are going to cause problems there? That sound of silence is right. That function, anytime you have a polynomial, polynomials, they are going to be continuous everywhere. So this is continuous everywhere on negative infinity to positive infinity. Great. When we take a look at our next function, we have h of x equals x minus the absolute value of x minus 2 divided by x minus 2. If we were to think about what that graph looks like, the top and bottom are the same, except for the bottom portion is does not have an absolute value, and the top portion does. So the top part would always yield a positive value. The bottom part would not. And so, what does this look like? Well, at 2, we would have an issue. And this function's not going to be defined at 2 because we'd have 0 in the denominator. If we have values smaller than 2, then this function looks like just a horizontal line at -1. For values larger than 2, it is a horizontal line at +1. Right? You could plug in values, convince yourself of that. Plug in 7. 7 minus 2, the absolute value of 7 minus 2 is 5. 7 minus 2 is 5. And so you'd have 5 over 5, which is just 1. Anything larger than 2, you're going to get 1. Something smaller than 2, so if you plug in 0. 0 minus 2 is -2. But then we're going to take the absolute value of that, so we'd have +2 on top. And we would still have -2 on bottom, which would give us -1. Right, so what do we have? Well, we have a discontinuity at x equals 2. Is that discontinuity removable or non-removable? So it's a jump, and it is non-removable. So our function is continuous on negative infinity up to 2 together with 2 to infinity, right? So we're just describing the x values here, and we're talking about the continuity, but we're thinking about how does it react along the y's. Are there jumps in the y's? And then this last one, we have a piecewise defined function. And so for a piecewise defined function, this function, j of x, it is defined to be negative x plus 1 if our x value is smaller than 1. So let's draw that. So we have negative 2x plus 1. And when we have a value that is greater than or equal to 1, we have x squared minus 1. So x squared minus 1. At 1 itself, if we were to plug 1 in, you'd have 0. So this is part of a parabola. So this is our function j of x. Is that function continuous? No, it is not. Where is that function discontinuous? It is discontinuous at x is equal to 1. There we have a non-removable discontinuity. Our function is continuous on negative infinity up to 1 together with 1 to infinity. So when I look at piecewise defined functions, the places where those functions glue together, those are places I have to be really, really careful about. We will look more at some piecewise functions in our next video. We're going to think about what do we have that causes potential issues for piecewise functions, and how can we analyze those more efficiently by using one-sided limits. All right, we will talk to you in the next video.